Yeah, okay. So welcome to lecture 2, which is interferometry. I click in to get it. There we go. So yeah, here's sort of the short version of what I wanted to cover today, which is talking a little bit about Fourier transforms, because they are going to be a critical part of everything interferometry related. Correlation of signals, visibilities, and all of that, getting into imaging. And I'd originally planned on getting all the way through imaging and deconvolution and into calibration and sort of some real interferometer considerations. And in the process of putting together slides, I've concluded that there's no way I'm getting through all of this in 2 hours. And so what I'd like to do, if there are no significant objections, is that I'd like to cover as much as I can today and then continue to try and finish this subject next time, because I think this is really sort of the meat of the course. And particularly the third lecture was going to be half radio emission mechanisms and half applications of radio astronomy. And truthfully, I haven't thought much about the applications lecture, and I think what I have thought about makes me think that that's going to be a course that's going to be, or a lecture that's going to be hard to be useful to everyone, because everyone has sort of different science goals. And so I'm kind of inclined to shorten the applications part, since that's harder to make sort of broad for the entire, for all of you, and spend a little bit more time on interferometry, which is kind of a meaty subject and one that I think benefits a lot from having a lecture rather than having sort of self-learning. So I'm going to go with that plan unless I get some strong objections. So let's launch into it then, starting with, okay, click into this, here we go, Fourier transforms. So this is just for a quick review, the sort of standard formulation of the Fourier transform. You have some function x of t, you pass it through this integral. You should be able to see my mouse, is that true?
Yep, you can.
Okay, great, thanks. So yeah, you pass some function x of t, put it through this integral with this Fourier kernel, which is this complex exponential. And the function of frequency, or omega, that you get out is your Fourier transform. And in principle, you can do exactly the same thing in reverse. You take your Fourier transform it, you push it through the positive version of this Fourier kernel, and it's supposed to restore your original function. And this comes up in a lot of different forms in radio astronomy. So last week I talked a little bit about beams associated with a dish in a phased array. That is also defined directly as a Fourier transform, as well as sort of the interferometry process is Fourier transform based. And so knowing Fourier transforms reasonably well makes it a lot easier to understand properties of how your radio telescope works, essentially, to the point where I've kind of committed a lot of the basic properties to memory, just in order to sort of very quickly be able to think about what happens in sort of the interferometric system when you change certain variables. So a couple of key properties of Fourier transforms. There's always 2 variables as a pair with opposite units, because they appear in the Fourier kernel, this e to the I omega t. Your omega and t variables always have to have opposite units in order to cancel out. So there's actually a lot of different pairs that can come up in sort of different environments. So time and frequency is the classic one everyone talks about in the textbooks. Position and wave number comes up in optics a fair bit. Angular position and number of wavelengths is the key pair for interferometry, which is a bit weird because they're both dimensionless. But and for the polarization fans, there's wavelength squared and Faraday depth. And there's many other pairs, but these are sort of the standard ones that we're going to talk about, at least in this course. In general, the input function and the output function can both be, or will be both be complex. The input function can be real, particularly if you're dealing with real measurements of voltage or some other physical quantity. But in general, the Fourier transform is a complex quantity or complex function. And there are certain symmetries that can actually affect sort of how that, sort of real versus complex behaves. And the Fourier transform can be extended to multiple dimensions. You can have 2D, 3D, or higher dimensional Fourier transforms. And this will be key in the sense that we can think of the sky as a two-dimensional surface, which means it then has a corresponding 2D Fourier transform. I've put an asterisk on this in the sense that the sky, so the Fourier transform assumes that your domain is nice and linear and infinite. So it's sort of in the Cartesian space. The sky, of course, is a spherical projection, and that causes all kinds of messy math complications, which we usually ignore by either dealing with a small chunk of sky in which we can kind of linearize our coordinates, or you have to do a much more complicated sort of version of the mathematics. There's a couple of sort of key properties that I think are worth remembering. So the first one is, for the first two are both linearity, which is if you build a function by summing up two or more individual functions, the Fourier transform of the sum is the sum of the Fourier transforms. And so you can build up arbitrarily complicated functions and know the Fourier transform if you know the Fourier transform of the individual components, is the first. Second is multiplication by a constant, so just a sort of a scaling and amplitude. That just falls right out because the integral is linear and you can just pull a constant out of the integral. Third, if your function is real, then this implies certain properties of the Fourier transform must be Hermitian. It must have the symmetry where the negative frequencies have to have the opposite imaginary component of the positive frequencies. And the reason this works is you can think of this as having to make sure that all of the imaginary components cancel out when you do the inverse Fourier transform to recover your original function. And lastly, if your original function is both real and has even symmetry with respect to the origin, the Fourier transform gets the same symmetry. There's a scaling law in terms of if you make your function sort of narrower or wider by attaching a multiplicative factor on your time variable, you get the opposite scaling in the Fourier domain. So if you make your function narrower, the Fourier transform gets wider, and vice versa. There is a sort of delay theorem. So if you take your function and you delay it by some amount in time or whatever your variable is, that manifests as changing the complex phase in the Fourier transform. You get this extra phase factor that depends on the shift. And so this is actually a really, really important theorem because it tells us that changing the position of your signal in whatever your variable is changes the phase in the Fourier transform. So the phase encodes information on position, is ultimately what that significance is. And lastly, if you have a convolution of two functions, the Fourier transform that is the product of the two individual Fourier transforms. Or all of these actually also work in reverse. And so if you have a function that's a product of two separate functions, the Fourier transform of that is the convolution of the two individual Fourier transforms. And so that comes up in a couple of places. There's a few sort of common Fourier transform pairs that pop up a lot, and so they're kind of useful to just have handy. The first one is that a delta function, the Dirac delta, Fourier transforms into a constant. It's just a flat function. Or vice versa, a flat function, Fourier transforms into a delta function. And I think the easy way to remember this is that if you have a signal that's perfectly flat, it has no oscillation, it has no frequency, it's just associated with the zero frequency. All your power goes into your zero frequency component, which is at the origin in your Fourier transform. Cosine transforms into two delta functions. And this one's kind of easy to see if you remember how you can write a cosine as the sum of an exponential and a negative exponential. You have those two exponentials, and so you can see how you would build that sort of as two Fourier components from the two complex exponentials. The rectangle, or the top hat function, comes up a lot. So this is just the function that's sort of the square pulse, and it Fourier transforms into the sinc function, the sine x over x function, and vice versa. And the 2D analog of this is if you have a circular aperture, which I spelled aperture wrong, I just realized. If you have a circular aperture, which, just a 2D function that's filled in a circle and 0 outside, that transforms into a particular Bessel function called the Airy disk. And this is your sort of classic mirror dish, circular lens kind of scenario. And so that's why the easiest model for any, the primary beam of a dish is just the Airy disk function. And finally, the other sort of very common one is that if you have a Gaussian function, it transforms into another Gaussian function. So it's the easiest one to remember, and it's one of the reasons that Gaussian functions are quite easy to work with in sort of Fourier analysis. It's also sort of subject to some of the previous theorems, so things like if you shift the center of the Gaussian, it applies the phase wrapping from the shift theorem. If you make the Gaussian wider in one domain, it becomes narrower in the other, kind of so on. And the other nice thing is that this property extends to higher dimensional Gaussians. So you can have two-dimensional Gaussians or even higher. Any questions on Fourier theorems before I don't jump into interferometry?
My question is kind of stupid anyway, because yeah, some of these actually sound vague to me because I've not, I can't relate to some of them, maybe because I've not done actual observation. I don't know where this actually comes in. Like, is it during the data reduction after you obtain your signal, or while I'm actually getting this signal out? I don't know.
So this will mostly come up in understanding what's going on with imaging, I think. And so this, if you're just going through a normal data reduction, you don't really have to know these theorems so much. It's just I find it quite helpful when I'm thinking about how does the signal for a delta function source look like, when I do the measurements in terms of measuring visibilities. If I have a Gaussian function, what are the visibilities for a Gaussian function? That kind of a thing. And so it's useful to understand the underlying principles, I guess, of the process. In terms of sort of mechanically going through a data reduction, it doesn't pop up that much, I guess.
Okay. So when do you necessarily need to image your radio data?
It's a critical step of interferometry normally. Is when it'll come up. And so that is probably the second half of this lecture is digging into that process and how Fourier transforms play into a role there.
All right, thank you.
Yeah, anything else? All right, so digging into interferometry, but starting with a little bit of sort of motivation, because interferometry, the theory is a bit of a slog, and I tried to condense it as much as I could, but it's going to be a bit of work to get to any kind of result that looks physically interesting. So I want to start by motivating why we're going through this, because every interferometry derivation I've seen just digs into the math without explaining why this is a good idea. And so in my mind, the motivation is that if you build a phased array or a big dish or something, ultimately you can point it in one direction at once. I mean, technically with a phased array, you can point in multiple directions, but that's with additional computational cost. But in general, you always have one direction that you have peak sensitivity in, and what you get out as a measurement is sort of your measurement of the flux density or the intensity in that direction. And so in order to actually map out the sky, you need to change your direction that you're sensitive to and basically scan the entire sky bit by bit to build up an image. And that seems kind of inefficient in some ways, because during this entire time, you're only sensitive to a small chunk of the sky, and all the emission that's in other directions is basically wasted. And so imagine, what if you could have a system that if you got some emission in, it would, rather than having to scan around to find where the emission is and how bright it is in different locations, what if you just got that information directly without having to go through the process of measuring every individual point? What if you could just get it all simultaneously? And that seems basically like black magic, and it kind of is. But interferometry gives us a method of kind of doing that with caveats. And so that's basically the motivation for it, is trying to create, or at least measure, all the information we need to create an image of the sky all in one go, kind of instantaneously in some way. And so this is sort of the goal that we're trying to get out of this derivation. So this all starts with correlation of signals. So let's start by considering a single source in the sky, just sort of a single compact source producing our good old monochromatic plane wave from last week, which arrives in our antennas, gets converted into a voltage signal. And so the net result, if we have two telescopes detecting this signal, is we get a voltage signal in each of the telescopes. And there might be some phase difference between them because the telescopes at any given instant will be receiving different phases of the wave. And then what we do is we're going to correlate them together. We're going to take, basically mathematically, this is the product of the two voltages integrated over some time interval. And when you put in your functions, what you get out is a function that oscillates twice as fast, it has twice the frequency, and you get a function that's purely dependent on the phase difference between the two. So there's no time dependence here. This is a cosine, so it integrates to 0 over a full cycle. And so the net result of this correlation, if you correlate over more than one cycle, is the time variation cancels out, and you're just left with something that's proportional to the voltage squared, which is then, that's in units of intensity, and it's proportional to the cosine of the phase difference. So here's the picture. Just sort of maybe clarify this a bit. So yeah, signal in some direction S hat is our directional unit vector. Two telescopes separated by a baseline vector B. Signal comes in, arrives at both telescopes. The difference in phase is due to this geometric time delay that we discussed last week. So you can express it in terms of the baseline vector dot product into the direction vector. And so this geometric time delay also defines your phase difference. And then you get this output product, which is voltage squared and the phase difference, which you can express in terms of the geometric time delay. And so the end result is that the output voltage, or voltage squared, encodes information on the power. I wrote flux, and I meant to say flux density. So that's on me, that's my fault. Encodes information on the power, but also on the position, because we have this cosine of phase. And the phase depends on the S direction vector. but we get ambiguities because if we think about this phase then comes from this b dot s term modulo 2 pi because it's a phase. All right, you lose if it's sort of, if we go back to this picture here, you know, there's some path difference here, but it could be that some path difference plus a full wavelength or plus 2 full wavelengths or 3 full wavelengths, n wavelengths. And you can't actually tell how many wavelengths difference this is. So you're basically losing a factor of 2 pi in phase. Yeah, so in principle, what you get out is you get this voltage in this cosine phase, but there's the ambiguity which comes from the 2 pi, and there's also ambiguity in the sense that cosine of phase for the same output could correspond to 2 different phases. Like you can think, and like the cosine function passes through 0 at 0 and pi, for example, or no, it's 1 at 0. Sorry, cosine passes through 0 at pi by 2 and 3 pi by 2. But anyways, like there's sort of 2 paces that can have the same value of cosine. And so one of the things you can do is if you manually add a pi by 2 phase shift between the 2 signals, and you then do the correlation, when you go through the math, in terms of going through this, if you just add an extra factor of pi by 2 in here, it transforms this cosine into a sine of the phase difference. And so you then have, if you do that, you have 2 measurements then. It's you have a measurement of v squared times the cosine of the phase difference, and a measurement of v squared times the sine of the phase difference. And so this removes the ambiguity of if you have sort of pi by 2 versus 3 pi by 2 phase difference. It doesn't remove the 2 pi ambiguity. And so what we can then define is this quantity that we're going to call the complex visibility, or script v, which depends again on voltage squared and these 2 correlations that we're computing. And so this is just a complex number with some amplitude proportional to v squared over 2 and the phase factor that we've defined. So a bit weird, but bear with me. So we basically get, you know, two voltage signals coming in, one from each telescope. We correlate them together. Well, we split them off. We correlate them together directly, and we correlate them, but we add a phase shift to one first. And then the outputs of those 2 correlations gives us a single complex number, which is our visibility. And so what this kind of gives us is from the amplitude, we know the flux density, and the phase, particularly now that we have the full complex phase, there's no ambiguities anymore, gives us position on the sky, because for any given phase factor, you can then ask what is the direction that the emission could be coming from. And because of this 2 pi ambiguity, you actually end up with multiple solutions for that. And so, you know, it could be that there's 0 pi phase difference, which put it sort of directly above the 2 sources, the 2 telescopes. There could be a 2 pi phase difference, 4 pi, 6, 8, etc. And then all of this shifts ever so slightly, you know, when your phase is non-zero. So if you measure a phase of 30 degrees, you shift it, you know, so much in one direction or the other. And so from this measurement, this correlation process, we've you know, isolated the position of the emission to one of these locations, and we've determined how bright it is.
Can I ask a question, if that's okay?
Yeah, please.
So when you first started with working through to derive the complex visibility, the first thing that you did was integrate over the 2. Yeah, so you integrated by multiplying them first. And so since the multiplication in the Fourier space is like a convolution, is that kind of like what that means to correlate signals? Is you're taking some kind of convolution of the 2 signals?
That's an interesting question. So right now we're not working in Fourier space directly.
Oh, okay. Okay. I just
Um,
wondered why you would integrate over the
to some degree, that's just the definition of a cross correlation is your,
Okay, so that's where that came from.
yeah,
That is just the definition of a cross correlation.
yeah, any cross
Okay.
correlation is you're sort of integrating over the length of your signal.
Yeah, but then I guess
measure.
I'm just trying to understand why you would multiply the two together.
Yeah, I mean that, in some sense, that's the definition of the cross correlation. The physical motivation is because it works.
Okay.
This is what I mean by you don't appreciate why we're doing it until you get to the end.
Okay. Thank you.
This is the problem with every interferometry derivation. None of the individual steps make sense motivation-wise. It's only the end result that actually makes you go, oh, that's why.
Okay, I'll try to keep that in mind. Thank you.
Yeah, but do keep asking questions.
Could I ask a quick question? Yeah.
Please, yeah.
Okay, so it's really basic, but you said, I think I missed it. I was writing something down and then I like didn't hear it. You said something about how after you get the visibilities, something, one of the variables corresponds to like the position on the sky. Which variable was that?
Yeah, that was the phase effectively. Phase,
Okay.
It's the phase difference measured at the two telescopes.
Okay.
And it's a really kind of bizarre concept. I spent a lot of time putting these slides together to actually stare at what I had written and think, wow, this is weird. Do I actually understand this? And I eventually convinced myself, but I had to stare a lot at various versions of this derivation. So if this doesn't make sense immediately, that's probably a good sign. And I definitely recommend
Just
spending
staring.
some time staring, as well as looking at other versions of the derivation.
Okay, I'll do that.
Because it's
so I want to know why is the product of the cross correlation called visibility? I mean, this is like the product of two voltages, right? Yeah, so why is it called visibility?
I don't actually know the origin of the term visibility. I know that it is used, but I don't have any sense for where the name comes from or what kind of meaning it brings with it.
Okay, like the first thing that comes to my head is that is linked to the imaging, like you mentioned earlier. So is this kind of helping us to the imaging process?
So there's no, well, I have to be careful what I say here. There is a relationship between the visibility and the image, and sort of deriving that relationship is sort of the goal of this whole derivation.
Okay.
So far, yeah, all I've done is define the visibility, and it's not clear why it's useful or what it even means, other than that it encodes something about brightness and something about position, as far as I've gotten so far.
Okay, all right, thanks.
Yeah. Anything else? Okay. This will slowly start to make more sense. So yeah, we have this sort of ambiguity. The sort of different positions are possible because phase, yeah, is intrinsically modulo 2 pi. And so this is sort of the representation in sort of this plane of the baseline here, or this direction. Since the sky is three-dimensional, this is actually fully sort of rotationally symmetric. Is the interferometer cannot tell the difference between a source that's sort of above versus one that's rotated, you know, by some amount along the baseline axis. And so having you know, just one baseline along one axis is not as good as it would first appear. I mean, you can tell that it's in sort of one of these circular fringes, but not which one and not where it is along that rotation axis. So three dimensions does complicate things, but it'll, thankfully, most of that complication goes away later on. So the biggest way of actually solving this ambiguity is you have multiple baselines, is you have more than 2 telescopes, and you make sure that the baseline vectors between the 2 telescopes have different lengths and different orientations. And the net result is that this set of fringes that you get for every baseline will have different size depending on the baseline length and different orientation. And so in principle, if you can, every one of these says, okay, the source has to be here or here or here or here. And then if you have, 2 or 3 or more sort of sets of information like that, you start to build up a more clear picture of where the emission is coming from. So a single baseline doesn't give us a lot. Multiple baselines starts to be useful. So we can also talk about angular resolution of these different fringes that we see for sort of this angular sensitivity. So our complex, or the phase difference between the telescopes is defined using this B dot S. And if we are looking at a source that's some angle theta from the horizon, then this just geometrically works out to being, we have this cosine theta from the dot product. And you can ask yourself, okay, if you have a source that's some slightly different angle, some delta theta, change in the location of your source, what is the change in phase? And that's sort of, you can just take that from the derivative, which turns the cosine into a sine. And so what it turns out is your sensitivity to different directions, your sensitivity to different directions goes as the baseline length and sine theta. So you're most sensitive to directions that are perpendicular to your baseline, essentially. So to maximize your directional sensitivity, you want your baseline perpendicular to the direction that the light's coming in from, effectively. And so and this also sort of expresses that there is sort of a geometric shortening effect, because all that really matters in terms of your angular sensitivity is sort of this projected length b sine theta, which is sort of the separation of the telescopes on the axis perpendicular to where the light's coming from. And so this sort of defines our angular resolution criterion in sort of the interferometric response, where if you sort of say, okay, what change in angle gives you a 2 pi phase difference? You just sort of set this equal to 2 pi, rearrange, you get this sort of lambda over baseline length sine theta. And so this baseline sine theta this is a sort of a classic resolution criterion or sort of resolution kind of equation. You have this lambda over d kind of equation, where in this case your d is the projected baseline length. Okay, so we've defined the visibility then for one source of emission in the sky. And in principle, we can just extend that to having emission all over the sky, having multiple sources of emission. And I'm not going to derive it here, but basically, if you go through the whole process, everything is linear, and you can basically just integrate over the space of possible directions. So you integrate over different direction vectors, over sort of the solid angle of the sky, the space of possible directions. And this is when you start to see some slightly weird behavior weirder than already was. So consider, for example, what happens when you have a source that's sort of extended on the sky, and it's big enough that some of the emission on one side is arriving in phase at the 2 telescopes, and emission on the other side is arriving out of phase between the 2 telescopes. And so particularly if it's a 180-degree phase difference, so in principle as a complex number, you have a complex number on one side of the emission in sort of one direction in the complex plane. The emission, the other side is in the opposite direction in the complex plane. You then integrate, so you're combining these, they cancel out. And so the net effect of this is if you have emission that is broad enough that it covers one full cycle of phase difference, it just cancels out to 0 in this integral. And so you get no net signal in your interferometer response. And so anything that is that size or larger vanishes effectively. Is anything that's large you don't get signal from, or the signal is mostly canceled out. And so the interferometer is only sensitive to emission that is smaller than its resolution effectively on a per baseline basis. And so this is a very kind of bizarre effect that we'll revisit probably next week. But it has some interesting ramifications for what the interferometer is sensitive to, what kind of things it can detect and what it can't. And so it basically emerges out of this integral under some conditions going to 0. Okay, so at this point we have a system of some kind where, you know, we have a baseline with the 2 telescopes. We measure, we get this visibility thing, and it encodes some position information in this phase. We can sort of make a more useful version of this if we start. We can sort of do a little bit more robust formalism, and so this is worth doing, I think, in the full 3 dimensions. Just to, you know, the 2-dimensional version is nice to sort of get a little bit of a picture of what's going on. The full mathematics, you may as well just suffer through the full 3 dimensions. So this is the coordinate system that we are going to be working in. We have some direction S0, where is sort of the nominal center direction that we're looking in, which is sort of, this would be the direction that you've defined, for example, your geometric delay to. It would be the direction, like the center at which you pointed your dish, that kind of a thing. And we're interested in emission that's coming in principle from other directions at the same time. So we have, you know, emission coming from different directions S, but we have centered our telescope on a direction S0. And we've defined this S vector in coordinates LMN. And we're working in this coordinate system where the W axis is towards this S0 direction that we've pointed our dishes in. And then we have a plane, this UV plane, which is the axis perpendicular to this. And so you pick some direction in the sky that you want to look at. That's your W direction. And then you have some UV plane that's orthogonal to that. And usually we define U such that it's oriented towards the east, and then V comes out towards the north, generally. Although not exactly east or north, depending on the direction you're looking in. It's 3D is messy. There's no way around it. So we have this, yeah, so our position, our direction vector, and we also have our baseline vector, which we've normalized by the wavelength, and this is UVW coordinate values in this coordinate system. So in the same coordinate system, we have this baseline vector UVW and a direction vector LMN. Yeah. And then we can define some patch of sky in a slightly bizarre way. So because we're going to want to integrate over the whole sky ultimately, and because knowing ahead that we're going to want to go into sort of a Fourier formalism, instead of defining the sky in spherical coordinates, we're going to treat the sky kind of like an infinite plane above the telescope. And so we can then define it as having sort of these linear coordinates, L and M, and a small patch of sky, a small piece of small at angle, d omega, can then be defined as basically DLDM, sort of the Cartesian sort of XY equivalent. And then there's a correction factor as you go away from the origin, or as away from straight up, because this is effectively correcting for spherical effects. As you go away from, you can make things look linear and Cartesian sort of at the center in the direction you're looking, but as you go out, spherical effects start to become worse and worse, and that's effectively accounted for in that term. You can actually derive this if you can treat sort of d omega as your usual kind of spherical polar coordinates and then try and transform into a Cartesian coordinate. It kind of comes out that way. So in this coordinate system, we start from this idea that the visibility then is the integral of the intensity distribution on the sky multiplied by this phase factor integrated over the whole sky. And then it gets ugly. So intensity, we're defining our direction vector in terms of L and M are our coordinates on the sky for directions we can look. D omega gives us this term. And we expand out B dot S as these coordinates based on the definition I just gave. And then we change things up a little bit. We pull out this omega n. So n, because S is a unit vector, it has to have length 1. So n, if L and M are our variables, then n has to be this in order to be a unit vector. So we're going to pull out this Wn term out front. And what we're left with is intensity as a function of position on the sky and what looks a lot like a Fourier kernel with two sets of variables, U and L as a Fourier pair and V and M as a Fourier pair. So L and M being our positions on the sky and U and V being the position of our baseline. So the relative position of the two telescopes. So as I said, there's this messy square root term is essentially corrections for trying to work in a Cartesian coordinate system when fundamentally we have a spherical system. And so as long as we consider directions close to the direction we're looking at, so L and M are small, then this term is usually small and this e to the Wn term is usually small. And so basically we want to neglect them because they're really ugly terms. And so fundamentally, as long as we keep our field of view reasonably limited, then we can do this mathematically. When your field of view starts getting quite large chunks of the sky to the point where spherical projection effects start to matter, then things start to break. So we do this, and then yeah, we can drop the square root term basically, pull this W outside of the integral, and yeah, this is a 2D Fourier transform, basically. And so we can say then is whenever we measure a visibility, what we're measuring is the 2D Fourier transform of the sky, modulated by this term, which usually is small, and it's kind of related to the geometric time delay. So I think we can ultimately correct for it. And so because every Fourier transform should have an inverse operation, we can then say, okay, we can turn this around and say that the sky, we can get the sky then, distribution of brightness, as the inverse Fourier transform of the visibilities, just by integrating over the space of possible baselines. Because remember that U and V are baseline length and orientation in our coordinate system. And so ultimately, this is what we wanted. We wanted a way to get the distribution of brightness in the sky. We wanted to know how bright it is and where it is, ultimately. And this is, in principle, the right tool for the job, because if you can measure these visibilities by doing the correlation of the signals from the two telescopes, if you can do this and then inverse Fourier transform it, it should work. And so that's kind of sort of mission accomplished for what we set out to do, except for all the complicating factors. So, which I'll sort of get to next, but before that, does anyone have any questions about this part of the derivation?
Not a question, but just because you can't see our faces, I wanted to say that was really great.
Seriously, everything makes so much more sense now, Cameron. And I've like gone through these calculations before and done like data reduction, and oh my God.
Is it? Okay, because I feel like I'm going through this really fast. I mean, it is.
Maybe because I've seen it before, but never really understood it properly. And now I understand it. So.
Yeah, I don't think that you're going too fast. And I think this has been extremely helpful.
Okay.
I actually have
Oh
a
my
question.
God.
Sorry. I just wanted to ask, when you said like interferometry has some kind of like, it's only efficient for certain things, what do you mean by like image smaller than what?
Sorry, could you say
said
that
it
again?
quite early. You said interferometry is only efficient for like image, it can only see image smaller than certain things. Is it like angular resolution or what is it?
Well, it's a function of your baseline length.
Okay, basically.
Let's see here. So that was sort of this, right? This idea of things being resolved out.
Yeah.
Yeah. Yeah. So
So
that
it's the
is
baseline.
Yeah. So basically, it's the length on the sky that you need to get a 2 pi phase difference. And so it kind of comes down, it comes down to this angular resolution criterion, where if you sort of take this equation and set it equal to 2 pi, then that tells you what baseline. Basically, you want this quantity to be less than 2 pi. So for any scale, any size, you just need to get a small enough baseline, effectively. Getting a lot of echo, so I don't know if that went through okay.
Yeah, I think someone needs to mute their mic because that was kind of hard to hear.
But yeah, okay. But did that make sense?
Yeah, that makes sense. Thanks. Yeah.
Okay. Anything else? Okay. Yeah. So yeah, the end result of all of this is we have this Fourier relationship. We measure visibilities, which come from the Fourier transform of the sky. We take measured visibilities. We, in principle, recover the whole sky. Biggest problem with this is this requires us to measure the entire parameter space of possible visibilities. So every possible length of baseline between two telescopes, as well as every orientation in sort of the plane perpendicular to your direction of propagation.
Also, is this for a single frequency, right? Yeah, that's correct.
Yes.
Oh.
Yeah, although in principle you can do this for as many frequency channels as you want simultaneously. Because all of this was basically predicated on sort of the monochromatic limit. Everywhere we're assuming some lambda, essentially, in order to have a well-defined phase. Is effectively it, and so there is an issue, going a little off script here. There is an issue of if you have too much bandwidth at a single measurement. If you have a wide band and you basically integrate over some large bandwidth and then do the correlation, that your wavelength is not necessarily well defined because it's changing with frequency, and the phase becomes smeared out. You can imagine integrating a signal with where the phase changes a little bit with frequency, and when you do that integral, over frequency, you start to lose information and you lose signal because you're combining things with different phases as complex numbers. So that gives you some weird effects. Yeah. So jumping a little bit into different wrinkles, I guess, on different aspects of this. One of these is there is a symmetry argument that comes up that's kind of useful to know, which comes from the question is, instead of correlating antenna 1 with antenna 2, what if we correlated antenna 2 with antenna 1? Which in principle is the same as asking, we have a baseline vector that goes from antenna 1 to antenna 2. What if we just made the baseline vector the other way? And if you just propagate through the math, baseline vector shows up in the phase. So you just flip the sign. So you flip the sign on the phase. And so in sort of, that's how it looks like in sort of the basic version, is all you've done is flip your phase vector around, but you've also sort of flipped your coordinate system. In sort of the full math 3D version, we can make the Fourier argument that the sky is real, intensity is a real quantity. Therefore, because of the Fourier theorems, the visibilities have to be Hermitian, the visibility function. And so if you flip the baseline vector, you flipped your coordinates in UV. And so to be Hermitian, it has to be the complex conjugate of what you measured from the forward baseline vector. And so you basically get 2 measurements for the price of 1. Although you're not actually adding any information, because the extra information is that I is real. But for every baseline you measure with some coordinate UV, you also measure minus U minus V, which is the same, but with the complex conjugate. So every time you sort of see visibilities, there's a sort of virtual pair, like a second visibility that's usually not written down because it's mathematically known what it is and doesn't really add much other than to enforce that this is real. So we can talk a little bit about the UV plane now. So this is the parameter space of possible baselines defined perpendicular to the direction the light's coming from, or the direction perpendicular to the direction you've centered on. You define a phase center direction. And so every baseline sits somewhere in this plane, effectively. And depending on the length of the baseline and the orientation of the baseline. And having defined this plane, we can then sort of talk about Earth rotation synthesis, which is a really cool trick, which is if you put yourself in the position of your source and you stare down at the Earth, as this diagram is, you see your baseline of your 2 telescopes with some length and orientation. And you wait a while for the Earth to rotate, and suddenly the length and orientation have changed. And so this means that the position of the baseline in this UV plane has changed as well. And in general, so you can sort of see over the course of like half a day, this baseline goes from sort of up-down oriented to horizontal and then back to up-down over the course of half a day. And so it basically ends up tracing out a circle or an ellipse in the UV plane. And so you can use this as a trick to get more measurements of different parts of the visibility function, because we want to measure this visibility function over the entire plane. And so our baseline moves through the plane, so we can, if you want, we can basically just wait as your baseline moves through the plane. You keep doing measurements and you're sort of collecting new information every time, because you're always measuring a different point in the UV plane. And over the course of 12 hours, you complete a half circle. And because of the symmetry argument on the last slide, you also know the other half circle right away. And so a 12-hour track will give you this sort of full circle in the UV plane. Oh, a slightly fun fact that I learned while I was researching these slides. The 1974 Nobel Prize in Physics was half for this technique. The other half was, I think, pulsars, something pulsar related. So there was a Nobel Prize in figuring this out, which is probably why it's hard. Okay. So this is all for a single baseline. So let's start to look at the effects of having multiple baselines together. And so this is the sort of 1D, 2D example. So if you consider an example where you have two telescopes at some distance, you go through this process, you measure the visibility, and what the visibility then is sensitive to is if you take a single visibility and inverse Fourier transform it, you get some sine wave. And so you don't know exactly what the sky distribution is. If you put in 3 antennas, you now have 3 different baselines. You have a baseline from 1 to 3, 1 to 2, and 2 to 3. So you have a long baseline, a slightly shorter baseline, and a much shorter baseline. And each of those has a different response on the sky. Coming back to this idea I had of sort of the different fringes at different positions. Is each of those has a different length because it's a different length of baseline. And so you have sort of 3 different, 3 different visibilities. So you get 3 different signals. When you add them together, you get something that has a little bit more directional sensitivity to it. You can tell it's in sort of, if you had a delta function source, this is kind of what it would return. If you put in 4 antennas, you get 6 baselines. And each of those baselines is measuring a different part of your visibility space. And when you combine them together, when you do the Fourier transform, it starts to combine into something a lot more coherent because you have more information. And so the net goal then with interferometry is you want to get as many baselines as possible, measure as much information as possible about the visibility space, and then that improves the information you have about the image. And so yeah, so the number of baselines scales quite interestingly. It's basically the number of antennas combined with the number of antennas it can match to. So you get this sort of n minus 1 sort of number of baselines. So it's roughly n squared when you get to large N divided by 2. And so for every new antenna you add, you end up adding more and more and more information. And so this is why it's beneficial to have a lot of separate antennas to get a lot of different baselines as opposed to having fewer very large ones effectively. And it increases surprisingly fast. If you have 7 antennas, you get 21 baselines. For something like the DRAO synthesis telescope, if you go up to 27 dishes like the VLA, you get 351 baselines at any given time. And if you go up to something like 63 antennas, something like LOFAR, you get almost 2,000 baselines. So the amount of information grows really fast. Although with the caveat that if 2 baselines are the same, they have the same length and the same orientation, then you're basically not getting any new information because you're measuring the same point in the UV plane with those 2 baselines. It can be beneficial in terms of calibration because you effectively have 2 independent measurements of the same thing. And so you can say, okay, how are they different? If there's any differences, it's got to be calibration error, that kind of a thing. But in general, you don't want that kind of redundancy. You want to get as much new information as you can. And so building a array pattern that sort of minimizes or prevents any kind of redundancy in terms of having baselines the same, it takes a little bit of effort sometimes. And it's surprisingly counterintuitive to actually figure out the correct, or sort of the best array configuration to make this work. Any questions on any of this?
Just a quick question. In terms of trying to find the optimal setup for baseline and antennas, do people use software for that?
So I've heard about simulations. So I think there was like some simulations for like SKA planning, for example, in terms of, I may have some slides on that. Let me see, can I skip ahead? I'll come back to this. I have some slides here that are relevant, so I think I'll come back to it.
Okay, cool.
But,
So many spoilers.
Yeah. But in short, is there are, I mean, there's not really any software in the sense that this isn't a thing that people do on a day-to-day basis. 'Cause once you've kind of built it, you can't generally reconfigure it that easily. So this is something you do kind of once when you're planning to build it. But it is a thing that people write papers about. People talk about different ways of optimizing configurations. If you say, okay, I have enough resources to build N dishes, I want to optimize for this parameter or that parameter, you can then talk about what's the best way to do things. And so there's a lot of science goes into that, I guess. And it's interesting to see how different observatories have solved this. Like the VLA is different than, LOFAR is different than ASCAP is different from all these other telescopes. So everyone has a slightly different solution because they're all trying to optimize for different parameters, essentially, is the long answer. Anything else? Okay. So in terms of sort of adding a few extra layers of realism to this, so as I said, we don't measure all possible baselines, even in the best possible case, because you'd basically need infinitely many radio telescopes, and not even the SKA has funding for that. So we have this limitation of limited information, and we can add that to our mathematical formalism by defining a measurement or a weight function, which I'm going to call W, which basically takes on a non-zero value for every position in the UV plane that we have a measurement at, and it's 0 everywhere else to reflect that we have 0 measurements or 0 information. And so you end up sort of defining it kind of like this, where you have this sort of, for every position of the baseline, you have a baseline ij with some coordinates UV. So at the position in the UV plane, you have a measurement, and you can assign some weight to that, which I'll come up maybe later today, maybe next week, about what kind of numbers you would want to assign for a weight, but in principle, just anything non-zero. And then the ensemble of those becomes your weight function. And how this incorporates into the mathematics then is we define that the sky is the Fourier transform of the visibilities. And this is a typo that I didn't have time to fix. The sky is the inverse Fourier transform, which doesn't change things much, but for technical correctness, the sky is the inverse Fourier transform of the visibilities. So what we can say is that the visibility function is defined over all possible UV values, but what we measure is just whatever our sampling function where we have the measurements is times the true value, which we don't actually know. So we can then say, okay, what happens when we inverse Fourier transform this? So that's the inverse Fourier transform of the product, which brings us back to our convolution theorem. So we can basically, it's the convolution of the product of the two functions. So the inverse Fourier transform of the visibilities, of course, is the sky brightness distribution. And we define the Fourier transform of our sampling function, our weight function, as what we're going to call the synthesized beam. Excuse me. So this is our synthesized beam, and this is ultimately the sky that we measure, or the result of the imaging process. Imaging being the process of doing this inverse Fourier transform on your measured visibilities. So when we get an image out, a measured image, what it is it's the actual sky image convolved with our synthesized beam, which acts as a point spread function, if you're used to sort of the optical use of that term. And so it basically acts to distort our view of what the actual sky brightness is. And this is a reflection of the limited information that we have from our measurements, ultimately. And this, I want to remind you about how much I hate the term beam because it comes up so often. So this is the synthesized beam. We are going to see more beams before we get through this. And so I want to point out that there's this really cool Python tool written by a former postdoc of Brian's, actually, Cormac Purcell. And he did, originally the virtual radio interferometer was actually a Java applet. Cormac rewrote it in Python and added some functionality. And this is a great tool to play with how interferometric imaging kind of works, the basics. And so I encourage all of you to install this and play with it. And I've taken sort of a bunch of screenshots to demonstrate sort of different aspects of this. So, so let's just start with a simple case. This is the Australia Telescope Compact Array, or at least five of these 6 antennas here. This is the UV plane showing the, or no, this is not the UV plane, sorry. This is the physical distribution of the baselines. So you can see the, or of the antennas rather. So you have the 5 antennas, 2 beside each other, and then 3 more spaced out. And so with this tool, you also have to set an hour angle range, sort of a time over which you're observing. So in principle, this is allowing for longer observations. And the net result, I've set this for a 4-hour observation, so between plus or minus 2 hour angle, 2 hours an hour angle. So a 4-hour observation with an east-west array. So you have basically east-west UV sampling, and then because of the Earth rotation, it gets, the vectors get rotated over as the Earth rotates. And so the net result then is you have 5 antennas, gives us 10 baselines. And you can actually sort of see that is if you count the tracks here, there's 2 tracks, 4, 6, 7, 8, 9, 10, and then the symmetric 10 for the backwards baselines. So we have 10 tracks for the 10 baselines where the system would be measuring sort of 10 visibilities for every integration. And you can sort of see that these are spread out in the UV plane because of the different baseline lengths. So these outer 2 are the longest baseline, so it'd be these 2 antennas with the furthest one. The next track would be these 2 with the next one. Third pair, those 2 with the closest of the outer antennas. And then we have the 3, we actually have 4 individual tracks, which would be, you know, the third antenna with the first, the third with the second with the first, and then the shortest baseline is these 2 really short ones here. So you can sort of see how every baseline and the vector between the 2 maps into different positions here in the UV plane. And the result then is if you Fourier transform this sampling function, you get your synthesized beam, and it's pretty horrifying. Everything in the image would basically get blurred out with this pattern. And the reason that this pattern is so tall is because we have very limited information along the vertical axis, along this v-axis. And so the lack of information we have transforms into a inability to constrain, because we can't tell sort of where along this axis the source actually is. So that's sort of this whole process. So here's the same configuration, but I've run it for 12 hours from -6 to +6, so half an Earth rotation effectively. And you can see it's filled in these circular tracks. It's just shy of 12 hours, so it doesn't completely fill in a circle, but just about. And now we've suddenly cleaned up our synthesized beam a lot better. It's a lot more circularly symmetric. It's actually elliptical, because the circle is not, it's not actually circular, it's elliptical, and the axes are a little bit distorted. And this comes down to projection effects between the declination of the source and the latitude of the telescope and stuff I don't really want to spend a lot of time on. Yeah, but you get a much cleaner beam when you have a much more symmetric set of measurements, effectively.
Hey, Cameron, could I ask a question?
Please.
So what is the difference between a synthesized beam and a dirty beam?
They are the same thing.
Oh my God, okay. Thank you.
which, you know, is a painful thing, especially in my mind, that you have two names for the same thing. And the reason the terminology tends to come up is we're talking about synthesized beams now because we're just looking purely at the imaging process. And dirty beams tend to come up more in the context of the clean algorithm, where you have a dirty beam versus a clean beam. And what the distinction between those is something I'll get to when we get to that part of the content, when I get to the slides on clean. So ultimately, yeah, they're the same thing. This is the short answer.
Thanks.
Okay, so yeah, so that's so the other thing that you can actually do with these sort of east-west arrays, these arrays that use the Earth rotation synthesis, is quite often they're built on rail. They put the antennas on rail tracks so that you can actually change the baseline lengths. You can move the antennas around and change the relative separations, the baselines, and so you observe for 12 hours. You know, maybe you do a bunch of fields over a bunch of consecutive days, and then you rearrange the telescopes to change their length, and now suddenly you re-observe the same chunk of sky, but with different baseline lengths, and so it lets you fill in the UV plane much better. And so this is what ATCA does if they have 4 configurations of different positions. So you get 4 times the 10 tracks, and so suddenly it's a lot more clean as a result. It's kind of hard to see how much the synthesized beam improves, but it is fairly significant.
Can you explain how did you get from elongated elliptical beam to a circular beam? Like,
yeah, and so that's primarily, well, that's a good question. I think what happened here is I changed the declination of the source between these. So this is me not doing a good job of being consistent. Or rather, it's me forgetting to explain the changes that I've made. I did actually, it is sitting here in my lecture notes that I am not looking at. So good catch, good catch. So yeah, so you get these interesting declination effects with baselines. Can I actually, yeah, and so you can kind of see, it's a little hard to see, but basically as you move your telescope to different latitudes, or you start to look from different declinations, the way that the projection changes as the Earth rotates tends to become different. And so if you have a purely east-west array, so a purely east-west array is good because it gives you sort of the most change in your orientation as the Earth rotates, but it has the disadvantage that you can imagine a source at declination 0. So it's hovering above the equator of the Earth. Earth is rotating. You have an east-west array. It's not changing in this axis anymore. As the Earth rotates, it's just changing horizontally from 0 to long. And so it would sit at V equals 0. A source on the equator would always be measured at V equals 0 by an east-west array. You would never get this sort of vertical baseline. And so east-west arrays are only good for sources near the celestial poles. Well, near. I mean, or rather, probably better to say they're bad at the celestial equator. But they do sort of okay everywhere else. But yeah, so east-west arrays, as you go to lower and lower declination, you get more and more elongation of the beam because of this effect. And I have data that shows that. I just did not put it in my slides. But I've seen this in data from the DRAO synthesis telescope, where as it goes to lower and lower declination, your beams get really ugly and long and gross. And so that's why most of the really expensive radio telescopes have north-south baselines as well as the east-west ones, so that they don't need to go through this process quite so much. Which was actually the next thing I was going to show, which was, yeah, this is the VLA with its 27 dishes in the 3 arms. And the 3 arms actually does some interesting things in terms of the baseline. So along each arm, you have a lot of set of baselines that are all kind of along the same direction along the arm. And so you see that as sort of 3 sets of spokes. So you have 1 set of spokes for all sort of the north-south baselines, and then sort of the southeast and then the southwest arms. And then all these points that are out of that are baselines that go from one arm to another arm. And so all of these baselines sort of sit in other parts of the UV plane. And so the nice thing about this is you, in an instant, so this is an instantaneous snapshot with no integration over time from rotation. In an instant, you get coverage over a very broad part of the UV plane. And so the VLA is able to basically do snapshot imaging, where you only measure for a few minutes and you can produce an image. And then you get a synthesized beam that's kind of gross, like this. And so this is a synthesized beam that has major side lobes. You have these spokes. And oh, I want to point out actually, so these spokes that you can see on the side lobe structure of the synthesized beam, note how they fall in between the spokes in the UV coverage, because these spokes in the UV coverage are directions that we have lots of measurements in, and in between, these are the directions we have very few measurements in. And so that's where the side lobes are worse, is where you have fewer measurements. And so with the VLA, you get this sort of it's a three-sided symmetry and then mirrored because of the symmetric baselines. And so you tend to get this effect. And so this is an example of exactly why synthesized beams can be a real pain, because suddenly you have artifacts with this shape through your image. Every real source is going to have this kind of star pattern around it. And you can imagine looking at something like one of these little blobs saying, is that a faint source or is it a side lobe of a bright source? And so this is why ultimately we need an algorithm like CLEAN, which will come up later. So this is the VLA in a snapshot. This is the VLA over a couple of hours. So you can still do Earth rotation synthesis. And then everything becomes a track and you have a lot of data, and suddenly everything is much better behaved because you're filling in all, or many at least, of those missing parts in the UV plane. So the beam starts to become better behaved if you get enough VLA time that you can integrate over longer periods of time. And so, as I was saying earlier, is you can have different configurations. This is ALMA, which has a much more complicated distribution of antennas. And the resulting UV distribution is really spread out and doesn't have a lot of clear structure to it. And the result of that is the synthesized beam doesn't have as much structure in it either. There is some kind of vague three-sided symmetry going on here again, but it's not as obvious. And so you get this result where, you know, a more complicated distribution like this is really good for snapshot images like this, where you don't want to integrate for a very long time to fill in the UV plane. And so that's why a lot of the newer telescopes are going to these kinds of configurations, because if they have the capability to get a measurement they want in a short time, they don't want to have to spend a lot of time integrating to fill in the gaps. They want to do these snapshots because they can, if they're doing snapshots, they can get more targets in the same amount of observing time. And so, yeah, arrays like ALMA and like SKA are doing kind of more of this sort of scattered distribution. Yeah, any other questions on that? Okay. So I want to sort of, in the spirit of adding additional layers, sorry, go ahead.
I want to ask if there is an application you are using to actually run this synthesis, like for different telescopes. Yeah. Is it something that we can access? Can you maybe share the link?
Yep. So the link should be on the website for this friendly virtual radio interferometer. So yeah, definitely install it, play with it, try different things. So what, like, there's a lot more that it can do than I've shown. Like, it can show you what happens if you put in different kinds of images, different sky distributions. and see, you know, how well does different antenna distributions recover different shapes on the sky. Like what happens if you have a very large thing, you can actually see if you put in long baselines how it can get resolved out, things like that. So it's a great tool. Definitely try it out.
Yeah, I found it on GitHub and I posted it on the Slack channel.
Ah, thanks. I think I linked it on the website. If I didn't, then I'll fix that. So yeah, absolutely great. Yeah. Yeah. So yeah, adding another layer of complexity is primary beam effects. So primary beam in this context is the beam of all the individual antennas or elements that you're correlating together. So if it's the VLA, that's the beam of a single dish. If it's something like LOFAR, it's the phased array because they phase up some number of antennas into a single station and then correlate stations to each other. Whatever the beam is of the thing that you're correlating is what we call the primary beam. And it has the effect of modifying the signal seen by your antenna effectively. It adds directional sensitivity, because so in the previous derivation, I had just assumed you could integrate over the whole sky without any problems. So this basically adds sort of your directional sensitivity. And it doesn't have to be the same for all of the antennas. You can have a different primary beam pattern. So this is important for VLBI, where you're correlating very different telescopes of different sizes, different construction, etc. So in principle, it can be the same if you're something like the VLA, or it can be different. And we're going to mathematically work through this as we're going to basically replace the input voltage, which is regular V, not the visibility script V, but the voltage is going to get modified as a function of direction by this antenna pattern as a function of direction. And I'm putting this under the square root for a reason. It's a little bizarre, but it makes sense at the end of the derivation. And so one of the things that has sort of been previously skipped in the previous derivation is this voltage is the integral over all directions. So now we have to integrate over all directions, but with this factor involved. And so we define the visibility between some pair of antennas, ij, some baseline. Previously, we defined it as the product. Backing up a step, I got this wrong. Right. So previously, we defined the visibility as just the integral over the intensity distribution on the sky. So instead, we're going to integrate over the product of the voltages as a function of position on the sky. I forget where the factor of 2 comes from, but I'm sure it's there for a reason. And
Isn't
so
a factor of 2 from the first derivation, like the first 2 pair of antennas.
I think it must be, yeah. I don't recall, but it's not important. Let's put it that way.
I and J is telescopes, right?
Sorry?
I and J is
yeah. I and J are any pair of telescopes in your array. So previously it was 1 and 2 for the 2 element. Now it's any pair. So yeah, the voltage from any as a function of direction is this beam factor for each antenna times the actual intensity distribution. Or I guess there's some, yeah, yeah. So we're modifying the voltage to be the voltage times the sensitivity. So you still end up, when you do the product, you end up with some voltage squared, which I've just converted back into intensity. So that's probably, that eats the factor of 2. So I've converted this back into an intensity unit. And then what you're basically just left with is the product of the 2 primary beam responses on the voltage. And So this just ends up as a product on your intensity. And this is still the Fourier kernel for our integral, Fourier integral. And so this is still just our 2D Fourier transform, and all we've done is tack on this factor in front. So when we create an image by inverse Fourier transforming, this should be an inverse Fourier transform again, you're just left with this extra factor of your primary beam response. And, right, so the reason for this is a square root is if your antennas are the same, then, you know, the square root and the squared cancels out, is all that's for. And so people like to express it, assuming that your antennas are the same, then you just talk about the antenna power pattern, which is the sensitivity in units of intensity and not in units of voltage, because there's a factor of a square in there. So that's a bit messy, but yeah, the net result is you just have this extra factor. So all you need to do then is you go through the image process, which is this inverse Fourier transform, and then you just divide by this sensitivity pattern as a function of direction from your beam, from your primary beams. And then that should again give you the brightness unaffected by your sensitivity pattern effectively.
So in a telescope, which one is the one that what is observable?
That is a good question.
I would assume the power pattern.
I think it probably ends up being the power pattern, yeah. Because that's like when you run a telescope as a single dish, your output result is power generally, because voltage isn't a signal that we can sort of directly interpret astrophysically. Voltages are complicated astrophysically. They don't have a clear interpretation, whereas power, like intensity units, do. So I think most of the time, well, so this gets a bit messy, because in principle, you can also have phase effects in here. And phase and power don't always play well with each other. So I think if you're doing a holography, it becomes ambiguous. I don't know. That's the short answer, is I don't know. Sorry. But it is a very good question, and one that should be borne in mind. Every time that I see a beam model, a primary beam model as an astronomer, it's always in intensity units. But whether it was measured that way, I couldn't say, I guess.
I want to ask a quick question. So is the primary beam the same as the antenna beam?
Yes, in the sense that, yeah, if your antenna is the signal producing the signal that you're correlating, then yes. You can talk about systems that have where the term antenna beam is ambiguous. So something like a phased array, where if you have 100 physical antennas, 100 wires collecting voltage, and you combine them as a phased array, you get one signal out of your phased array. And so you would then use that one signal to correlate with another phased array. And it's the combined signal of the phased array. The phased array will have a beam. It'll have a array beam or a station beam or whatever, and it's that beam that matters. It's not the beam of single antenna out of 1,000 or whatever. It's the combined beam, which is a bit weird.
Okay.
So yeah, the short answer is it's the beam of whatever signal you're correlating, and whatever system calculates that. And so that's why primary beam tends to be used in interferometry, is because it abstracts away all of that complication. Oh, echo. But, okay.
All right, thanks.
Okay, yeah. So yeah, so the primary beam acts as this multiplicative factor, decreasing your sensitivity effectively, and so decreasing the amount of flux that you see in the image. So you basically just divide it onto, pull it onto the other side of the equation by dividing, in principle, to get the true intensity. Main thing that you want to note here that messes this up or makes it complicated is that, so this also amplifies the noise, because in principle, we haven't talked about noise really, but it is going to be present in your visibilities. It'll be present in the Fourier transform of your visibilities. And so the noise then gets divided by this position dependent quantity. So your noise becomes position dependent. Usually sort of some of the Fourier theorems result that noise tends to be uniform across the image before this, where, I mean, the actual noise value is random, but the statistical distribution is uniform across the whole image. You have the same RMS everywhere, generally, the first order. But then as soon as you do this, you're dividing by some number, and that pumps up the noise by the same amount, and so the noise becomes position dependent. And the second sort of consequence of this is if your beam has nulls, it has about places where it goes to 0, you can't recover that sensitivity, because you'd be dividing by 0. If your sensitivity is 0, you have 0 information in that direction, and you just can't recover that information no matter what. And so so what typically tends to happen is people will mask out regions where the beam is 0 or close to 0 and say, well, there's no information here. And in the places where the beam level is very small, usually at the edges, where you only have 10, 20% sensitivity, now your noise has been boosted by a factor of 5 to 10. And so I have an example actually from my own PhD. This is a terrible LOFAR image, probably one of the first LOFAR images I ever made. And this very poor calibration, which is why there's a lot of ringing and stuff around different sources. But this is an image with no primary beam correction at all. And so the noise is mostly uniform, but you can see at the edges, there's almost no sources. All the sources that are there are very faint. There's bright sources in the middle, faint sources at the edge. That's not of astrophysical origin. And so if you correct then for this primary beam sort of sensitivity drop, suddenly the sources at the edge are equally bright, as you'd expect. There's no reason that chunk of the sky should be brighter than the others. So you have, all the sources are uniformly bright, but the noise has become a complete mess. And you can see here, this is regions where the beam is close to 0, and the imager has actually masked that rather than put in infinities. But in the regions around that, this would be if the imager has cut out regions of below 10% sensitivity, then just outside this is like 15% sensitivity. And so the noise here is 7 or 10 times higher than at the center. So this is something to consider, when you start producing images, that okay, you will have this position dependent noise after doing the primary beam correction.
So with this positional dependence of the noise, is it generally true that this is mostly affecting the edges of your image?
Yes, because the edges of your image, well, usually by definition, you've put the center of your image at the center of your primary beam, because you have pointed at some chunk of sky, you've centered your telescope on it so that your primary beam is centered on it. So you have peak sensitivity in the center, and then you go out to where you have lower sensitivity. In theory, you can have cases where you are not imaging the same direction that your primary beam is centered on. This can happen in certain edge cases. And so you can have a case where it's not always going to be kind of radially outwards where the noise increases. But that's kind of special cases. Yeah. Anything else? Okay, I am actually getting, no, this is about as far as I thought I'd get. This is good, 20 more minutes. So let's talk about imaging, since I promised this was coming up. So based on the definitions that I've given so far, we have this I measured, which is the convolution of the real sky with the synthesized beam. In principle, because this, in terms of the mathematical formalism, these are all continuous quantities. They are continuous functions of position on the sky. And in principle, if you could do the inverse Fourier transform as a continuous thing, you would recover it all as smooth functions. But we are working on computers, and computers want everything to be discretized. We're working on, we're producing digital images, so everything is going to be quantized onto some pixel grid, of course, right? Just as we're used to with CCD images. But there is a fundamental difference between an interferometer image and an optical image. And nobody ever talks about this, and it took me forever to figure this out. This is not in any textbook, but I think it's really important. So I'm going to spend a few minutes on this, about how exactly these are different. And so on this diagram, this is just a 1D case that extends generally to 2D. So starting on the left, let's think about an optical image from a CCD camera. So CCD has some grid of pixels. Light falls onto some pixel or another, gets added up. Every photon gets counted. And so an optical image is intrinsically a measurement of a flux density. I mean, recall that flux density is the integral of brightness over some surface area. And in this case, the surface area is the chunk of sky that each pixel sees. So each pixel is integrating some area of the sky corresponding to that pixel's area. And so the result of an optical image is always going to be a flux density. So yeah, I thought I'd consider in this case a unresolved source, so a source that's very compact, and it's being broadened by your synthesized beam or your point spread function of your optical telescope. So in the case of an optical image, the number of photons, if you sort of add up over the whole source, you get the number of photons coming from the source. It doesn't really matter how it's distributed, but it's going to be a constant, basically. So if you were to take your camera and make the pixels half as big, then suddenly you have the same amount of signal split out over twice as many pixels, or 4 times if it's 2-dimensional. So the same signal split up over 4 times as many pixels, the flux density per pixel should be 4 times smaller. But the integral is the same because you still have the same number of photons. Radio images, or particularly interferometer images, drastically different. So a radio image is intrinsically, it is the intensity distribution of the sky. So it is not integrating in any way over the area of a pixel. So the visibility, the inverse Fourier transform of the visibilities gets you an image or an intensity distribution. And the imaging software is not integrating over your pixel. It is calculating the value at the center of the pixel. So you have some continuous function for intensity, and the imager is plucking the value at the very center of the pixel. So it's a very different process. And so you can sort of see it is picking out the same intensity value as the underlying distribution, but only in a single pixel, at the exact center of your pixel. And so if you were to double the number of pixels you have, or double on each axis, so you have 4 times as many pixels, you're sampling your function in more places. And the integral, or the summation over pixels, is not conserved. And so if you try to integrate over your source to get the flux density, it's actually a slightly more complicated thing, because it depends on how you've sampled your image, how many pixels you have, and how densely you've sampled. And so you end up with a more complicated equation where you have the intensity in each pixel, times the area of the pixel on the sky, the solid angle, and then you have to normalize out by the synthesized beam to get the actual flux from the source, because the shape of your beam determines the shape of the response at each of the points, effectively. And so we have this sort of fundamental difference then in terms of how you sort of treat these quantities. Like in optical images, you can just aperture integrate, so like do sort of, you know, just add up values to get sort of the total flux. And with the radio, we have to think a little bit more about the beam shape and how many pixels we have. In principle, if you're interested in the intensity of the source, you can almost just read it off the peak pixel value. And this is a thing that people often do, is you just take your highest pixel and you know, say, this is the intensity of my source directly. Although there are some caveats with that I actually didn't make a slide for, so that might be next week. But yeah, in principle, things like flux density, which comes from integrating, are a little bit messier. So I think that's something I don't see talked about, but it messes with how you think about radio images in terms of being able to think about how signal happens when you change your pixels and stuff. Any questions on that? Okay, I'll assume you're properly confused because this took me a long time to actually internalize.
Yeah, I'm definitely confused about what's happening.
Me too. Sorry.
No, this may be the reason why no one talks about it, is just because it's too confusing to think about. But it's, yeah. I mention this because this irritated me a lot when I first kind of came to this realization. Because there was a point where I was trying to just calculate integrated fluxes of sources or something. And suddenly it's like, wait, no, I can't do it in the obvious way. And I can't use like optical software to do stuff.
Can you explain what do you mean by at the center of the pixel value? Isn't that what we're doing with the optical as well? Like,
no, because the optical is taking every photon that falls on that pixel in the camera, right? It can fall in the center of the pixel. It can fall in like on a corner or the edge. As long as it's inside the square of the pixel, it gets counted as a photon.
oh, okay, that's what you mean. Okay.
And so with a radio image, you could in principle have all kinds of weird structure in the intensity distribution that occurs between pixels and you'd never actually know. And so it's a bit of a bizarre thing.
I have what might be a super basic question that would help with my confusion.
Please.
So I can understand how with an optical telescope, if you have a CCD, it seems like super intuitive to me why you have pixels and how they play into your imaging. But I don't have any intuitive understanding as to where pixels even come into play with radio interferometry.
Yeah, and so they come in because we have to discretize. Is we can't produce a continuous quantity in a digital computer, ultimately. Is a computer has no way of storing a arbitrarily complicated continuous function, ultimately. And so when we want to deal with something in sort of terms that a computer can deal with, we have to break it up into discrete numbers that can each be individually stored and manipulated.
So I guess it's like after you've collected all of the voltages and you've done the cross correlation, then you turn that into digital information where it gets discretized into pixels.
Yeah.
Okay.
Yeah, and it's a bit weird because if you think about it, your visibilities are quantized because for every baseline you get one number out per integration, and so you have a finite number of visibilities stored. But when you go through the Fourier transform, the discrete Fourier transform, it takes in theory at least, you could take a discrete number of measurements and still transform them into a continuous function. The Fourier transform allows you to do that in terms of the mathematical formalism. And yet the computer doesn't allow us, is what it boils down to.
That actually helps. Thank you.
Yeah. Anything else?
I know when I was playing around with CASA for a while, you have to choose your cell size, like essentially choose a pixel size, which felt maybe not arbitrary, but they didn't give a good intuition, a good kind of reasoning behind how to choose it. They just kind of gave you a guideline. Is that something we'll get into eventually here?
Yes, I feel mildly clever with myself now because somewhere in the upcoming slides, I actually talk about it.
Awesome, thanks.
So,
Amazing.
I feel like I anticipated a question. Good for me. All right. Yeah, so imaging on a computer. Oh, chat pop up. Is that a question? FFT resolution. I don't think it's intrinsically connected to FFT resolution. There will be a relationship with FFT resolution as of, well, this slide that I've just popped up. But I don't think what I discussed previously is quite directly related. But I'd have to think about that. You have very difficult questions for me, Thomas. Yeah. Okay. Oh, another chat. I shouldn't have closed that. Okay. Right. So the imaging process, since we are stuck on a discrete system, is ultimately we want to create a n by m pixel image. It could just be n squared, you know, if you want a square image. We want to do this from the Fourier transform of the visibilities that we have. And so as Shannon just pointed out, the number of pixels and the size of each pixel, the cell size, is set by the user and is semi-arbitrary, but the next slide has some comments on that. And so because we are measuring on a grid, the fast Fourier transform, the FFT, is the most efficient way of doing this. And the FFT transforms or creates an n by m grid of pixels of outputs from a n by m grid of inputs. And so all we need then is to take our visibilities then and to stick them onto this kind of a grid. And baselines aren't going to fall onto this grid naturally because the baseline lengths are continuous quantities. The baseline is wherever it is in physical space. And the spacing of points in the UV plane depends on your cell size because there's FFT rules. Excuse me. FFT rules, it's for if you want your spacing in the image domain to be so large between samples, then the spacing in UV coordinates has to be some reciprocal of that. And that's, I'm not going to get into detail aspects of FFTs, but there's these kinds of rules. And so baselines aren't going to fall onto this grid. And so there is some gridding process that basically takes the visibilities sort of as sort of continuous quantities wherever they're located and maps them onto this strict pixel grid in the UV plane in order to do the FFT. And it may happen that some like groups of visibilities could actually get grouped together into the same point in your UV plane, get averaged together. There may be points in the UV plane that have 0 visibilities. So there's this kind of a process, which usually we don't see, but is computationally expensive, so people talk about it sometimes. And it introduces some small level of error because you're shifting visibilities around and such. So you basically, create this n by m grid of visibility measurements, and you push it through the FFT algorithm, and the end result is this n by m image. So yeah, so in general, the number of pixels and the pixel size is a user thing, but in practice, there's usually some connection to your observing parameters that you want to use. So pixel size is usually such that you want 3 to 5 pixels across your synthesized beam width. And to explain that, actually, I can go back to this image So you can look, if you look at the radio image here, this is an image that has about 3-4 points across the width of the synthesized beam. And you can see that it's not actually picking up the peak. This measurement is sitting a little bit off the peak, and so it's reporting a slightly lower intensity. And it doesn't really give you the shape very well, just from having four measurements. Whereas if you have more measurements, you actually get a clearer sense of what the shape is and where the peak is and such like that. And so, so there's this sort of factor. You want at least 3 to 5 pixels across your beam in order to get a clear sense of what the shape of the curve is. And this is called the oversampling factor in some cases, because you are sampling more densely than your resolution. Ultimately, your resolution is the width of your synthesized beam, but you want to have several pixels across that in order to have a good measurement. And so an oversampling factor of sort of 3 to 5 is kind of the minimum. Some people like 8 pixels across the beam. You can do more, and in principle that's good, except that it starts to increase the computational expense and increases the size of your images in terms of how many pixels you need. So it gets computationally and memory intensive. I once created images with an oversampling factor of about 20, and those looked ridiculously smooth, but it was a waste of memory. And so the total number of pixels that you need is usually, you want it to be enough to cover the full width of your primary beam, because that's the area of sky that you're sensitive to, out to maybe the first null where you have minimum sensitivity. But sometimes you want to actually go a little bit further out to sort of the first side lobe of the primary beam, because you can have bright sources that are in the side lobe of the beam, so quite a ways off center. But if they're really bright, the interferometer still picks it up, and it can cause problems in your image. So sometimes you image out much further than that. And so you can generally calculate the size of your synthesized beam from the longest baseline. And so, you can figure out your resolution that you expect in your image and figure out what cell size you need to get your number of pixels. And you can generally figure out the size of the primary beam from the size of each dish in the array or whatever. You can estimate that, and then work out for your pixel size how many pixels you need to cover. And so those are sort of how you can calculate that. I put an asterisk in around sort of having enough pixels to cover the primary beam. In VLBI, things get to be a little bit messy and complicated, because I mean, the point of very long baseline interferometry is the very long baselines give you amazing resolution, so you have very small pixels. And if you image the entire primary beam with your very tiny pixels, you might have hundreds of thousands of pixels across, and then square that. It's too computationally expensive. But in VLBI, there's also different kinds of effects that you can get, things like time smearing and bandwidth smearing, different kinds of decorrelation effects, which actually tend to be a function of how far away from the center of your image you are. So VLBI images are kind of limited in size by that and not by the primary beam. But the details of VLBI are outside of the scope of what I want to cover. So yeah, we've hit 5 o'clock. I just want to very quickly talk about, no, I might actually stop here because this is going to take a couple minutes. So this is maybe a good spot to stop for today. Are there any questions?
I do have a quick question about the slide. So it seems like these are 2 different conditions that you can use to choose your pixel size, like your sampling of pixels. Like one is using either the synthesized beam or the primary beam, which I believe are different, right?
Well, but there's 2 free parameters at play and two input conditions. So the 2 parameters are pixel size and then how many pixels. And the two inputs then are the synthesized beam and the primary beam size. And so you basically have two unknowns and 2 functions to constrain them.
I see. Okay, thank you.
Anything else? Okay, so yeah, since it is 5 o'clock, I think I will stop there. We got through actually more than I kind of expected, but so I think, yeah, we got through everything up to basically imaging here. So I think next week I already have the slides on weights and clean, and some more sort of details on how imaging tends to look in practice. So I will go through those next week. Some on calibration, and then I want to get into radio emission mechanisms and kind of radio physics a little bit. So a little bit of kind of the analysis side once we actually get some data is kind of the goal, to kind of move to that. Yeah, so yeah, keep an eye on the Slack channel, I guess, for any updates. Same time next week. I am starting to work on the second homework exercise, if anyone's doing those. Not sure when that'll be posted, but hopefully beginning of next week, maybe tomorrow. Yeah, otherwise, yeah, thanks for coming.
Thanks, Cameron.
See you next time.
That was awesome.
Bye.
Bye.
Bye, everyone.
Yep.